Welcome to the second part of our fifth class time series of lecture videos for the notes. In this video we'll start going over the naming handout that will have been posted in your Canvas for organic molecules. So all hydrocarbons are molecules with only carbon and hydrogen atoms. Alkanes are defined by carbon and hydrogen atoms being connected by single bonds. Alkanes can be linear or branched. Oftentimes we write them with these valleys and peaks from left to right, like pentane or propane. I could have just put another carbon on pentane and I would have reached hexane. Or you can twist the molecule around in the bond line structure and make it look a little different in the plane for your molecule. Hydrocarbons can be branched, as alluded to above. Here we have 3-methylpentane, and I will get to how we decided that there was a methyl group at carbon number 3 and why we put this sort of name down for this branched alkane. This particular one would be classified as 4-ethyl heptane. So there are rules for naming, and we'll get into those shortly. Alkanes that are linear or branched are characterized by the formula CnH2n plus 2. Cycloalkanes, of course, are different. Here we have cyclopropane. It's a 3-membered ring, highly strained. Here we've got cyclohexane, which kind of lacks strain. It's a 6-membered ring. And there we have cyclobutane, another strained ring, which is composed of 4 carbons, so 4-membered ring. A general formula for cycloalkanes is CnH2n, because a linear alkane needs to lose 2 hydrogen atoms in order to form a ring. So we need to be familiar with some definitions in these for these molecules. A primary carbon, that is symbolized as 1 with a little degree sign, has only one other carbon bonded to it. All the hydrogen atoms bonded to a primary carbon are referred to as primary hydrogens. So, for example, ethane has 2 primary carbons and a total of 6 primary hydrogens. It will be important for us to know these definitions when we get to our chapter on radicals. A secondary carbon has 2 other carbons bonded to it, and we symbolize it with a little 2 with a degree sign. So this is propane. There are 3 carbons in it, and it possesses 2 primary carbons and 1 secondary carbon. And of course there are 6 primary hydrogens, and the secondary carbon has 2 secondary hydrogens. We can go ahead and point these out. That's the primary carbon right there. That's another primary carbon. This is the one that's the secondary carbon. So hopefully that's clear for this particular molecule. So we'll continue on. A tertiary carbon, symbolized as 3 with a little degree sign, has 3 other carbons bonded to it. This 2,4-dimethylpentane possesses 2 tertiary carbons, 1 secondary carbon, 4 primary carbons, and of course the corresponding 2 tertiary hydrogens, 2 secondary hydrogens, and 12 primary hydrogens. You could even explicitly write them on there. So here are the tertiary hydrogens. Here are the secondary hydrogens. And then we could go ahead and write all these methyl groups out explicitly to cover our primary hydrogens. So a quaternary carbon is symbolized as carbon number 4 with the degree sign, has 4 other carbons bonded to it. So this 2,2-dimethylpropane possesses one quaternary carbon, 4 primary carbons, and of course 12 primary hydrogens. In terms of naming the linear alkanes, characterized by CnH2n plus 2, table 2.5 in your text gives their names as well as their formulas, and some interesting physical properties for comparison's sake: melting point in degrees C and boiling point in degrees C. So methane, of course, is a gas at room temperature. It freezes at minus 182.5 degrees C, pretty close to the temperature of liquid nitrogen. And it boils at negative 161 degrees, or 161.7 degrees C. Ethane, it has 2 carbons, and our melting point might be a little lower. Our boiling point is it's liquid all the way to minus 88.6 degrees C. Propane has 3 carbons, butane 4 carbons, pentane 5 carbons, hexane 6 carbons, heptane 7 carbons, octane 8 carbons, nonane 9 carbons, decane 10 carbons. These are always more difficult, going from 10 carbons to the 20 carbons. Undecane is 11 carbons, dodecane is 12 carbons, tridecane is 13 carbons, tetradecane is 14 carbons, pentadecane is 15 carbons, hexadecane is 16 carbons, heptadecane is 17 carbons, octadecane is 18 carbons, nonadecane is 19 carbons, and our 20 carbon hydrocarbon molecule is icosane. And if you followed along with the physical properties, it is kind of interesting. Propane, we've all probably used propane barbecues. Our boiling point is minus 42.1 degrees C under normal atmospheric pressure. Of course, the propane tanks are pressurized, so you can hear and feel liquid sloshing around in the tanks, which boils off very easily once we open the tanks, and comes out into our barbecues, where we can use it to cook things. Butane, of course, there are butane lighters. Now we're getting pretty close to 0 degrees in terms of a boiling point, transition of liquid to gas. Our melting point has come up substantially as well. Pentane is a liquid at room temperature. Of course, it's very volatile, as is hexane. These are hexane and pentane are standard solvents that we organic chemists use to purify things. Heptane, we just keep increasing our boiling point. Now we're at 98.4 degrees C, as well as our melting points. Octane, nonane, decane. Wow, I mean, our boiling point is well over boiling, the boiling temperature of water for decane at 174 degrees Celsius. And so one might ask, why are our boiling points increasing in temperature as we get add carbons to our linear chain? And of course, the forces that hold these hydrocarbons together are van der Waals forces, also known as dipole-dipole forces, or London dispersion forces. So what does that really mean? It means that as we grow our molecule, we get more and more clouds of electron density from additional carbon and hydrogen bonds, and those clouds can be polarized. So when a molecule bumps into another molecule, it can form an instantaneous dipole. So the electron cloud in one molecule sort of pushes the electron cloud in another molecule over so as to form a sort of negative part and a positive part on the molecule. The more and more of those dipoles you have, the better those molecules stick to each other. And so by the time you're at decane, I mean, you've got a pretty high boiling point. And it's kind of fascinating to know, nature takes advantage of these van der Waals forces. So I'm sure most students have seen geckos. Geckos can stick to the wall and to the ceiling as they climb up with their little feet. How do they do that? Are their feet sticky? Well, actually their feet possess very, very tiny hairs, and quite a bit of them. And those hairs have a very high surface area. And those hairs form van der Waals forces with the wall or whatever it is they are climbing on. And those forces are strong enough to allow the little creature to defy gravity. So it's kind of interesting how nature uses van der Waals forces. At any rate, you should know the names of alkanes from 1 to 20 carbons. So that concludes this video. I will see you in the next one.